In this video, we're going to apply what we've learned about parameterized families of differential equations and bifurcations to the model we learned earlier, logistic growth with harvesting. So let me remind you how that model worked. Logistic growth meant that we had a population, and the differential equation that controlled the population's growth, well, if it was just what I've written so far, that would be unlimited growth. That would just keep growing and growing and growing. But the logistic model asserts that there's some maximum that it will not go past, or if it started above it, it would come back down. And that involved this factor in the differential equation. And just as a reminder, if you do the phase line, what you'll find is you can see if you set this equal to 0, p would be 0 is 1 answer, and if p were equal to n, you see you would have 1 minus 1. Right, so we have, of course, if you start with 0 of the population, then you're always going to have 0 of the population. But if you start with n of the population, you also stay at n, and that's the carrying capacity. And if you start less than n, the arrow here, if you plug in a number between 0 and n, the arrow goes up. So it will go up like this and level off. So it grows fast at first, but then it levels off asymptotically approaching this n. That is sort of the population level that it wants to be at. And as I said, if you start above n, it actually will come back down, because that's higher than the environment can really sustain. Okay, so that was the logistic growth. So we have the n is the carrying capacity, k is the natural growth rate. That the k just sort of determines how fast these lines get to that horizontal line. All right, but then, and we did look at this in a problem or two, what if at the same time humans are harvesting this population? So the typical example here is fish. Fish would normally grow according to a logistic model, more or less, but if humans are also fishing the area, then that's an additional decrease of population that has to be accounted for in the differential equation. So now we have dp dt equals k p 1 minus p over n, and then minus, because we're taking away fish, and at some rate. So let's say c is the harvesting rate, the number of fish per unit time that is being fished out of the ocean or river or lake or whatever we're talking about. Okay, so this now is our differential equation. Now let's take a closer look at that differential equation, look at the phase lines for different values of c in particular. Okay, so here we go. So we're going to start with this differential equation. Now let's find the equilibrium solutions. This is the equation we have to solve. Remember, we're solving for p. P is the variable we're trying to solve for. Now if we multiply this out, it will look like that. We can multiply through by n just to clear out that denominator, and we get, and then let me put the p squared in as the first term. So we get minus kp squared plus knp minus cn equals 0. Okay, so we have a quadratic, and so we solve it using the quadratic formula, and we get p equals, it'll be negative kn, that's our b, plus or minus square root of k squared n squared minus 4kcn, that's a 4ac, and it's all over, what would that be, minus 2k, 2a, right, but a is negative k. All right. Now because we have a square root, we are going to have potential for bifurcation, because depending on what's under the square root, we may get 0 or 0 or 1 or 2 solutions, right? So we want to take each of these in turn. What would give us one solution? Well, we would get one solution if the thing under the square root came out to be exactly 0, right? Because then it would be plus or minus 0, which doesn't make a difference. So we would just get one answer. So we would get one solution if k squared n squared minus 4k cn were equal to 0. All right, so k squared n squared equals 4k cn. Now I'm going to assume that both k and n are positive numbers, that they could never be 0. Obviously n can't be 0 or we don't have a problem. I mean, we don't have a, a model. And also k, same thing, k can't be 0 or nothing's growing either. So it makes sense that k and n are greater than 0, so we can divide through by k and n. So I get kn equals 4c. So I get, and I'm going to put c on the left here, c equals kn over 4. So the harvesting rate would have to be kn over 4 to get exactly one solution. Okay, what that would mean is, if I go back to the quadratic that we were trying to solve, I can see that there's a negative coefficient in front of the p squared. So the graph of this guy would be a parabola opening downward. And you get exactly one solution if that parabola just touches the axis, right? So that's how you get one solution. Okay. And so the phase line would be, we would have one solution. The solution, by the way, would be, let me write that in, the solution, remember we're assuming that the square root came out to be 0, so it would be minus kn over minus 2k. I guess the k's cancel and the negatives cancel. We would just get n over 2. So we would have an equilibrium at n over 2. And now, where do the arrows go above and below? Well, you can see from my picture, which is easier than trying to actually work back with the expression, that if you're a little bit less than n over 2 or you're a little bit greater than n over 2, your parabola is down in the negative region. So this is giving a negative number. So we would have down arrows. So there's the phase line for the population of fish if we have this condition of the harvest rate equaling k times n over 4. Okay. Now, let's think about the 0 solution possibility. Let's see. Do it on a fresh page, but I'll flip back and forth as necessary. We will have 0 solutions. That, of course, will happen if we get a negative under the square root, so that nothing exists here. It's the same algebra, but with a less than 0, right? So we actually, and then remember I flipped the left and right hand side over here, so actually at the point here it would actually be greater than. C would be greater than kn over 4. So we will have 0 solutions if C is greater than kn over 4. What that looks like in terms of the parabola would be still that upside down parabola, but it just never got up to 0. Okay, so no solutions. All right, now the phase line, which is what we really care about. Well, we would have no equilibriums. We have no solutions, so there are no equilibrium solutions to the dE. And so I don't have any dots to draw. And I can see that my parabola is negative the whole time. So the phase line is kind of boring. It's just downward. Okay, and then finally we get 2 solutions. Obviously that would be if the thing in the square root were positive, right? Then I would have plus the square root, and that would be an actual that would be a number greater than 0, or minus the square root. So we'd get 2 different answers, And this is what it would look like, this big quadratic formula expression. And the condition on C would be, again, you would have a greater than here, greater than, and then this is where I flipped it, so that would be less than. So C less than Kn over 4. In terms of the parabola, that's where the parabola does creep over the axis and we get our two answers, right? And in terms of the phase line, sorry, I'll put it over here. Yeah, we will just get two solutions. Not exactly sure where they are. Again, it would come from whatever this expression gives us. All right. And I can see that if I'm below the lower equilibrium, so that would be like over in this region, I'm getting negative, so that's down. In between the two solutions, I get positive, so that's an upward arrow. And then on the high end, I get down, so yeah, down arrow. Okay, so let's put it all together. I have my three separate phase lines, but let's put it all in sort of one bifurcation diagram. Okay, so here I'm going to draw a sequence of phase lines for different values of C. My middle one is going to be that key one, which is C equals Kn over 4, because that appears to be where the bifurcation happens. And we saw that the phase line there was a single equilibrium point, down arrow, down arrow. We saw that if C was bigger, we had no solutions and we just had down arrows, just all down. And if C were less than Kn over 4, that's when we would get two solutions and it was down, up, down. And yeah, maybe another one here. I think they would get a little bit spread out as we go. I could do, if I did one more. I think the bottom equilibrium could go below 0 and that would be fine, but it's still down, up, down. Okay. So here's the situation. So the bifurcation occurs right here. The critical harvesting rate of Kn over 4 is the difference between two different kinds of behaviors. Now let's talk this through and analyze this and see what the actual behavior. Let's relate this back to what's going to happen to the fish. If we're in this region, if our harvesting rate is not too big, right, then think about how the solutions will work. Let me isolate one real quick. Okay, so I've just, any one of these three guys I've just kind of reproduced over here, and I just needed a little room next to it to draw some pictures. Yeah, right, at either of the two equilibrium solutions, the population would stay stable. If you started in between, it would go up to the higher one. If you started above, it would go down to the higher one. And that's all good for the fish population, right? So the fish population, if you start anywhere between here or up, even with the harvesting, you're going to hit this intermediate level of number of fish, and it will be stable in the long run. Now, if you start below the lower equilibrium, you've got a problem. You will go extinct. The fish population will go extinct. It'll drop to 0 and further down. Okay, but that is if you're below the lower one, and the lower one might already be a pretty low population level. So, maybe the fish population was already pretty tenuous to begin with. Now, if you're in this region, I'll just draw right here. Clearly, you go down. There's no leveling off happening in this region, and that's when C is greater than Kn over 4. So we're our C is too big. We're harvesting too much, and we drive the fish population to go extinct. So this is extinction, and it's bad. This is good. This is an okay level of harvesting where you're not going to drive the fish population to extinction. Right? Now the one right on the edge here is a little tricky because yes, you have the equilibrium solution, and anything that starts up here will go down toward it. But we have an issue because if you're a little bit below, you will go down to extinction, right? Now you might say, well, okay, so as long as the population starts above that equilibrium, you're fine. Yeah, but this is a node because we have down and down on both sides. So yes, mathematically speaking, this will level off at this equilibrium, which is okay for the fish. But this is a mathematical model, and nothing is exact, of course, right? So, imagine a little, very choppy thing. And if this, even just because of some randomness and some choppiness, dipped below the equilibrium, well, now that down arrow on the other side is going to take over, and you will go extinct. So although from a strictly mathematical point of view this seems like it would be okay, this is an unstable situation, and you could very easily, just through the real world randomness, dip below the equilibrium, and then you're in trouble. And of course that's even assuming that you can keep this this right on the nose harvesting rate of kn over 4. Of course that's not possible either, right? There'd be some variation over time with that. So what you really want is to be a little bit away from this critical bifurcation moment of harvesting. You want to make sure your C isn't too close to this number at all, and that you're sort of safely in this region, and then everything's good. Now, just as a final note, let me just say that this is as simple a model as you can make that takes into account how a fish population may grow on its own and how harvesting would work. Notice, especially with the harvesting, we just literally had a constant harvesting rate, which is not 100% realistic at all. But what's interesting is even in that simple model we have this interesting behavior, right? And not completely predictable, just without getting into the details of the differential equation. And so you can expect that if you added more realism to the model, you might get more surprises and more interesting behavior than even this is showing. So this is, yes, a very simplistic model, but even the simplistic model is indicating that there's sort of this critical point after which something drastically different happens. You can be in a good situation, and then if you just increase C by a little bit more, suddenly you drive the species to extinction. Okay.